All right, so we're doing our notes on electricity and Ohm's law, and we're going to start off here with just a simple definition that electricity is the flow of electrons. Electricity is the flow of electrons, or moving electrons. And I'm going to abbreviate electrons with an E negative right there. You can do that as you wish. In fact, maybe I'll just put a definition over here. E negative equals electrons. There's two kind of types of electricity that is very common. You've got electric current, which we tend to think of if you've got a battery hooked to a circuit or if you're plugging something in to an outlet. So we got electric current. And then there's another type that's called static electricity. Static electricity is a buildup of electrons. You've done this when you've walked across a carpet. Here you are, you're walking across a carpet, scraping your feet on the carpet, and then you go touch something and you get that little zap. What's happening is, basically, you are scraping electrons. This is the simple definition. You are scraping electrons from the outer parts of the carpet, and they're building up on you. And now what happens is you start to build up a negative charge because you're scraping more and more electrons on you. These electrons, once they're on you, they're not going anywhere. And that's the static part. The term static means not moving, in case you weren't sure about that. Not moving. So then when you get enough of these, you scrape your feet long enough, or you're in the park and you're sliding down the slide, when you reach out and touch something, here's your hand reaching out and touching, okay, here's the doorknob, right? So you're at a door and you touch that doorknob, and all of a sudden, all these electrons, almost instantly, they flow off of your body because there's hardly any electrons, extra electrons over here. They're going to go from the buildup and they're going to jump over, and you get that little zap of electricity. So we've got electric current, which we tend to think of with batteries, hooked up into a circuit. Here's a little light bulb. That's a light. Okay, you've got a flow of electrons going this way. You plug in to your appliance and you get electrons coming in. Question is, how do some things cause more static buildup than other things? I think the best answer I can give you is some things, if they have a lot of friction, like scraping your feet on the carpet or sliding your blue jeans down a slide, you're causing friction, and that can cause electrons to build up in one place. If there's not a lot of frictional stuff occurring, it's not going to happen. So let's see. And we're going to do some terms here now. Oh, you know what? Yeah. Okay. Under electric current, so I'm going to call this, I guess I'll call this one Part A, or Roman numeral, Part A, not Roman numeral 1, but Part A. Alternating current. So kind of under the electric current part, you get what's called alternating current. That's what you get when you plug in to the wall. And what alternating current means is that when you plug into the wall, for a moment, you've got electrons pushed towards you, and then in the next moment, the electrons are pulled back from you, almost in a sawing kind of a motion back and forth. And I believe this is 60 hertz. Which means 60 cycles per second. When you plug in something, you've got these electrons pushed towards you and pulled back 60 times every second.
What's the point of pullback?
I beg your pardon? What's the question?
What's the point? Why did it need to be pulled back so I can't have direct current?
So the question is, why? Now, the next thing we're going to talk about here is direct current. And there's some advantages to direct current, and then there's some disadvantages to direct current. One of the disadvantages for direct current is that it's very difficult with DC, they call it for short, to be able to keep the electricity strong over great distances. So it turns out that by using the seesaw motion, it's much more efficient at transmitting electricity over great distances. So,
extension cord, like great distances, like power lines, or great distances like.
talking great distances like power lines. If you're trying to power a city, they started with DC systems, direct current systems in cities, and they were very difficult because the lights wouldn't work well. When they did alternating, it worked. But I want to get these notes, and I'm recording here, so let me get that. So this is electrons are pushed back and forth. And we're going to draw a little graph here. And we're going to label this voltage over here, which we'll define in a moment. We're going to label this 0 volts right in the middle. We'll have -1 volts, which really just means which direction the electrons are flowing. And then a +1 volts, which means they're flowing opposite directions. And let's see, as best you can, let's make this little graph into 4 sections. And so we're going to plot what they call it's a sine wave. So what happens for a little bit in an alternating current, you get electrons are beginning to be pushed towards you, and then it begins to slow down, and then at one point, now the electrons are being pulled back the opposite direction, and this pattern repeats. And if it's the standard electricity we get at home, it's 60 times a second that you get this little sine wave, this little forward and back, forward and back. So you can think of this as the forward part and the back. I'll say the backflow of electrons. And we'll label this time over here as 1, 2, I guess I better put 3 and 4, and I guess we'll call this seconds down here. I should have labeled that before. So this is what, if you could graph and see, the electricity when you plug into the wall, you'd be seeing it coming towards you and back at you very quick. The other type is called direct current. Okay, up here, AC, and then direct current, or DC. This is what like batteries do when we hook up batteries into circuits. So I'm going to draw a battery here that represents kind of what we're using. Because what happens is the electrons flow one direction out of the battery and back. And so electrons are pushed only one direction. Electrons pushed only one direction. So we're going to redraw our graph over here. Label that 0 and 1 and -1. Thank you. Let me know. Sorry that I got off the screen there. So there we go. This is time in seconds. And we got the same amount of time. We got 1, 2, 3, 4. So now if you were to hook up electronic devices to measure this, here's what it would look like with direct current. Your graph would be this. I'll make it kind of thick so it stands out. You would have, if it's a 1 volt battery, 1 volt, the electrons are only going one direction. Electrons, one direction. Simple to generate and use, but this doesn't work well when you're transmitting over great distances. a battery. That'd be kind of a good representative. This is the plus end of the battery, that's the negative end of the battery. Oh, and this is voltage here. So now we need to define these terms. There are three factors involved in electricity. Number one is voltage. V, voltage. And this is a measure of how hard electrons are being pushed. A measure of how hard electrons are being pushed. Whoops, pushed. And typically it's measured in volts, or for us, millivolts. So volts, millivolts. And that's what we'll see on when we're working with the voltmeters. So you've got a device like a battery, it's going to be pushing it out. If you've got a 5-volt battery, it's pushing like 5 times harder than a 1-volt battery. So the next one, number 2, is resistance. And I believe it's omega is the symbol that is used to represent resistance. And this is a measure of how hard it is to push electrons through a material. So it's a measure of how hard it is to push electrons through a material. And this is measured in, the symbol is omega. I'm pretty sure that's omega, hopefully I'm not wrong, but they call that ohms. I believe it was named after a scientist that worked it out. Ohms. He might have been a guru because he might have sat around going Om. His mantra could have been Om. Okay, aha, okay. We're almost done here. I think you're going to like this last one. Last one is current, and the symbol is I. And this is a measure of how many electrons are flowing through a material. So it's a measure of how many electrons. Oh, no, I shouldn't say that's through.
Is it like how many are going through it per second or something?
Yes, that's right. And it's going to be measured in amps or milliamps if you've got small little systems. And that's usually an A or milliamp like that. And I think we showed that to you on the voltmeters before. So we've got how hard electrons are being pushed through something. We've got how hard is it to push them through. Some materials it's really easy to push electrons through, other ones it's more difficult. And if you hook, and it can be if you have a whole bunch of appliances hooked up in a circuit, the resistance goes way up. And then the current is a measure of how many electrons you've actually got flowing through there. And the last one, Ohm's law. And then we're done. Ohm's law. V equals IR. Veer. If you're a fan of equation triangles, you can put V in the top, I and R down here. So if V equals IR, what is I equal to? Current. And what is resistance going to be equal to? So I'll have you and your partners work that out, and I'll stop this here now.